So, as an example of this parallel fault simulation, parallel pattern fault simulation. So, what we do is that we take this example, and now you see this same circuit that we were discussing previously. Now, here this fault free response for this P1, P2 and P3. So, these three patterns, the fault free responses are like this, that A, B, C being this. So, these are the fault free responses. Now, when this fault F is there, so what we are doing is, in one shot we are simulating three patterns simultaneously, P1, P2 and P3. Then in the presence of fault F, we are again simulating the three patterns. So, when the fault F is present, then this P1 and P2, these values are different from values of A, they are different in P1 and P2, but for P3 it is same. So, it is 1 1 1. So, this P3 it does not change. So, this way if we do a simulation, you see the finally this P1 and P2 could detect this particular fault, okay, F, particular fault F could be detected by them. Then we go to the fault G, and again for three patterns we simulate the for fault G, and see that this response is finally turning out to be 1 here. So, we have got this output different from the good circuit. So, this fault getting detected. So, this is the parallel pattern fault simulation. In parallel fault simulation, where we are trying to simulate for multiple faults for the same pattern. Now, in case of parallel pattern fault simulation, so we are trying to simulate multiple patterns for the same fault. So, fault is dropped as soon as detected. So, this is one of the very important advantage, because previously in parallel fault simulation, the problem was that until and unless all W minus 1 faults are detected, we could not drop those W minus 1 faults in none of those faults. So, but in this case, since the simulation is done for a single fault, so we could detect if as soon as the fault is detected, we can drop that particular fault. So, it is best for simulating test patterns that come later, where fault dropping rate per pattern is lower. So, later on what will happen is that fault dropping pattern will fault dropping rate will reduce. As I said that initially even some random patterns will detect a good number of faults, but as we go beyond some point, then this fault pattern the fault dropping rate will reduce. Newer patterns will not be detected, will not be able to detect very complex faults, or very we call it resistant faults. Disadvantage, it is not suitable for sequential circuits, because sequential circuit it has to go over number of cycles. So, that is one problem. Next, we look into another fault simulation strategy, which is known as deductive fault simulation. So, it is based on logic reasoning rather than simulation. So, we are not really simulating the circuit, but we are doing some logical reasoning over the test patterns and fault list. So, what we do, a fault list Lx is attached with signal x. So, every signal line x has got a fault list Lx attached to it. So, what does Lx contain? It contains set of faults causing x to differ from its fault free value. So, this is basically the faults in the circuit that could be detected if you look at point x. Okay. So, a set of faults that cause x to differ from from its fault free value. And another thing is the fault list propagation. So, based on the fault lists of input, we try to propagate the fault list to the output using logical reasoning. So, we will see how this thing happens. Say we have got an AND gate. Okay. So, when we have an AND gate, suppose we have got an AND gate. Now, in this AND gate, maybe certain faults could be detected at line x. So, we have got Lx associated with it, and we have got y where it is Ly. Now, depending upon these lists Lx and Ly and the values that we have here, so it may so happen that at output some of these faults will propagate. It will be possible to propagate some of these faults to the output. So, for example, for AND gate we know that the controlling value C is 0 and the inversion value is I is also 0. So, this is basically as we have seen earlier, this is a truth table representation of this logic functions, a more compact version. So, it is the controlling value and this is the inversion value. If any of the inputs are having controlling value, then the output is C XOR I, and if the value is different, if none of the gates are having controlling value, none of the inputs are having controlling value, then the value of a gate is C bar XOR I. Now, this is the formula. So, if all gate inputs hold non controlling value, that is none of the inputs are stopping the other value to propagate. Like when we are talking about AND gate, if none of the inputs are 0, that means it cannot stop, one input cannot stop the faults associated with other input to propagate to the output. So, if that is the situation, that all gate inputs hold non controlling value, then the list of faults associated with line Z that could be observed at line Z is given by union of this Lj, where j belongs to I is the set of gate inputs. So, whatever faults you could have associated with the inputs of the gate, so you take the union of them, and that becomes a part of Lz. And there is something more, which is Z stuck at C XOR I. So, this particular symbol is used for representing Z stuck at C XOR I. So, as I was taking the example of AND gate, so assuming that both the inputs are 1, so they are non controlling value, they are holding non controlling value. So, whatever is Lx and Ly, they will come to the output, plus we can check at this point the Z stuck at 0 fault. So, this fault can also be this fault also can be observed if we can look at the circuit at point Z. Now, so this is the case when all the inputs are holding non controlling value. On the other hand, if at least one of the input holds controlling value, then there is a problem, because it will not be able to see all the faults. So, which faults will propagate? If I have got the S as the set of inputs holding controlling value, then so you have to take intersection of this. So, whichever faults are common between all those controlling points, that minus the union of all these faults that are at the gate input other than the controlling value, other the faults at the non controlling value that are there. So, this minus this. So, this becomes the first part, and the second part is Z stuck at C XOR I bar. So, that can be detected. So, this way we can we can see what is this Lz that can be computed, and it can be propagated through the circuit. So, this is, you see that we are not doing any fault simulation here. So, we are not simulating the circuit logically, but we are going through a set of logic operations. We are doing some set operations and trying to construct the set of faults that could be detected at different points in the circuit. So, when this Z becomes the primary output, then at that primary output we have got the set of faults that could be detected. Okay. So, what is this what is the procedure? So, start with the collapsed fault list, look at the next pattern. So, apply next pattern, do a fault free simulation, propagate the fault list, and then we delete the faults from the faults on the fault list, and if the fault set become empty, so then it will go back. So, in this case, this say P1. So, P1 is this so LA. So, with A, since it is a primary input, so we have got the set of faults that can be detected here is A stuck at 1. Since P1 has got 0 1 0 as the pattern, so if I can observe at this point the circuit, then the A stuck at 1 fault can be seen by this. Similarly, this point if I can observe, then I can see B stuck at 0, this point I can see C stuck at 1. Now, since this is an say this is an OR gate, and OR gate one of the input is 1, so that is a controlling value. So, in this case, so we get at the output this B stuck at 0, E stuck at 0, these two faults. So, B stuck at 0 is coming from this controlling input. So, there is only one controlling input. So, if we look into this formula, so it is a intersection of this controlling input. So, that is nothing but this is only one. So, this is B stuck at 0. Then we have got this then this minus this. So, there is nothing. So, nothing comes from this that second part, and then this E stuck at 0, because E is becoming 1 in the fault free circuit. So, E stuck at, so this becomes the fault test associated with line E. So, this way it continues, like say here this particular example. So, what is happening is that this is a NOR gate, and you see that both the inputs are 0, and for a NOR gate 0 is a non controlling input. So, we will get this L of k as L of h union L of j union k stuck at this 0. Okay. So, that value will be detected. So, this is the formula. So, if you combine this use this formula, so ultimately this line k, it can detect all these faults. Okay. So, that is detected. For pattern P2, so it was 0 0 1. So, 0 0 1. So, it could detect this it could detect this new fault B stuck at 1. So, which was not there in the previous case. Since this A stuck at 1, H stuck at 1, these faults are already detected. So, they are dropped from the fault list. So, we have got this B stuck at 1 fault, and this C stuck at 1 is also covered. So, C stuck at 0. So, these two are the remaining faults that could be detected by this particular pattern at this point. Accordingly, we propagate, and since this is an OR gate and 1 is the controlling value. So, this comes at the output, and then C stuck at 0, and then this E stuck at 1 is already covered. So, E stuck at 0 is already covered. So, that is why this E stuck at 0 does not come at this point. This fault does, though this pattern also has the capability of detecting E stuck at 0 at this point. However, that is not counted because the fault has been dropped. So, this way we proceed, and then we can see that ultimately in the K it can detect the fault C stuck at 0. So, this way we can figure out the faults that are detected by different patterns as we proceed through the pattern set. Then P3 value was 1 0 0, then it was detecting A stuck at 0. So, here we just show this gate condition that one input is 0, another input is 1, and since this is a controlling input, this 1 is a controlling input for a NOR gate. So, I have to follow this formula Lj, the controlling input pattern set, controlling input fault set minus non controlling input fault sets, that is Lj minus Lh union K stuck at 1. So, this F stuck at 1, J stuck at 0, and K stuck at 1. These are the faults that could be detected by pattern P3. So, this way this deductive fault simulation works. Okay. So, this is a set of so basically set manipulations and following a set of rules for deriving the output fault list for input fault lists of individual logic gates. Advantage, it is very efficient because it is processing all the faults together and all that. So, it is a very good, it simulate all faults in one pass. So, it is not that we have to do it again and again. Disadvantage, not easy to handle unknowns. So, this is another one problem, because at some point if you get an U, then it is not mentioned, like how can we handle an U situation, unknown situation. Only for 0 delay model timing. Okay. So, basically if we have got some finite delays, then of course these faults will also take some time to propagate to the output, but that is very difficult to catch when exactly it has propagated. So, we can this deductive fault simulation, it will not help you that way. And memory management problem is there, because there are set manipulation. Ideally for every line it has the potential to detect all faults in the circuit. So, as a result, if you are following a simple array based implementation, then you have to have some huge arrays associated with each line. If you are using some linked list based manipulation of these faults that can be detected at a particular line, then that linked list manipulation is again other issue. So, this way we have got both advantages and disadvantages of this deductive fault simulation. Next, we will look into another policy which is known as concurrent fault simulation. So, it says that simulate only differential parts of the whole circuit. So, as sometime in logic simulation we have seen that if we are from one pattern to the next pattern, so we identify the portion that is changing, and for that part only we will do the simulation. So, here also the same condition. So, if we see that some part of the circuit is going to change their values, then that part only will be simulated. So, it is an event driven simulation with fault free and faulty circuit simulated all together. So, the event driven simulation means that if the circuit changes, some part changes, then only the output of that gate will be simulated, and it is also some sort, it is concurrent, because fault free and faulty circuits, they will be simulated together. So, it clubs the advantages of parallel simulation and this event driven simulation policies. So, concurrent fault list for each gate consists of set of bad gates, that is, if something went wrong with the circuit, then what happens to this gate. Okay. So, it may not be due to some problem at the input of this gate alone, it may be problem due to some problem somewhere else in the circuit as well, but if due to that fault this gate's behavior changes, then that will call a bad gate. So, along with good gate, we remember all the bad gates for every gate that we have in the circuit. So, initially we have got only the local faults, okay, but as we propagate the faults from previous stages, this set of faults will increase. As a result, the set of bad gates that we have, so that is going to increase. So, all those gates will be simulated parallelly. Again, the events, they can be classified into a number of cases, good event and bad event. So, events that happen in good circuit, so they are called good event. So, basically some input pattern changes, due to that some gate inputs will change. So, that is called a good event. So, this good event, they will affect both good gates and bad gates, because the input pattern is going to changing. Then there is some bad event. So, events that occur in the faulty circuit of corresponding fault. So, if due to some fault some event has occurred, some output has changed from 1 to 0. So, for example, if certain gate has been assumed to be stuck at 1, as a result the input of some other gate has changed. So, that other gate that we are talking about, so that needs to be simulated. Okay. So, that way, so that is the events that occur in the faulty circuit of the corresponding fault. So, that is a bad event, and it will affect only bad gates. So, good gates need not be simulated again. Diverge, so addition of new bad gates. So, if new bad gates get created in the process, that is called diverge, and converge is the removal of bad gates whose IO signals are same as corresponding good gates. So, if we find that some of the gates behavior is becoming similar as good gate, then there is no point simulating that or simulating that output further. So, that will call a converge, as if the bad gates have converged onto a good gate. So, that bad gate need not be considered. So, the flow of the algorithm is simple. So, it again starts with the collapsed fault list, get the next pattern. So, apply next pattern, then analyze events at gate inputs, execute events, compute events at gate outputs, more events. So, then it will again analyze events. So, that way it goes. However, as I was telling that there is there are a number of gates associated with each physical gate in the circuit. Okay, one of them is a good gate and others are bad gate. So, how that thing happens? So, let us see this example. Suppose we have got this circuit. Now, initially A, B, C, all of them are unknown. Now, we apply the first test pattern P1, which is 0 1 0. Now, when we have got 0 1 0, then this input may change if this A is stuck at 1. So, if this A stuck at 1 fault is there, then this gate will behave differently like this. So, from u equal to 0, if it is if this gate pattern is, if this fault is if this input is stuck at 1, then this gate will behave in a different fashion. So, this becomes a bad gate for this gate. Now, similarly, this OR gate, when it is C stuck at 0 fault will be coming. So, then this will behave in a bad way. So, that is another bad gate for this. Now, this inverter, so this is J stuck at 0. If J stuck at 0 occurs, then this point becomes an this becomes a bad gate. Okay, so, this way it identifies the set of bad gates for pattern P1. Now, we take up pattern P2, and then we see that when we propagate, we see that many new bad gates have got created. Okay, this effect of this line C it was here that C stuck at 0. So, that effect, that bad gate effect has propagated through this line and come to G2. As a result, this one G2, so this creates another bad gate C stuck at 0. In that case, one input is 0, other input is 1, and C stuck at 0 fault is there. So, it generates the 0 as the output. So, that is the faulty output. So, this way it can for pattern P2 we can identify the set of gates which are going to be bad in this new situation. For P3 we see that this is propagating further, and you see that at this point we have got this C stuck at 0 coming to the primary output. So, we drop C stuck at 0 from the set, that is wherever C stuck at 0 gate was there. So, all those bad gates are dropped because they are detected at gate G4. However, similarly this A stuck at 1, so this is also dropped, okay, this because this is detected at a primary output. So, this is also dropped. So, we have got this thing that while P3 simulating P3, so we have found that these faults or these bad gates propagated up to this K. So, those bad gates can be deleted. Advantage, this is efficient definitely, but disadvantage is the memory problem, because the concurrent fault what is happening is that I need to remember a number of bad gates for every good gate. So, when we are trying to do that, so I have to remember a more number of gates, so more amount of memory and runtime complexity. Then there is differential fault simulation, which combines the merits of this concurrent fault simulation and parallel pattern single fault propagation technique. So, both the techniques are combined together and we get this differential fault simulation. So, it says that simulate in turn every faulty circuit and track only difference between faulty circuit and last simulated one. So, that is why it is using the term differential. So, inject differences as events and then use an event driven simulator for doing the simulation. So, that is a differential fault simulation. So, concurrent and this parallel pattern single fault propagation technique. So, first this for the good circuit. So, we simulate this for this pattern P1, P2 up to Pn. So, this G1, G2 is the first. For P1, G1 is simulated, then we insert fault F1, then it finds out what are the faulty responses for every fault. So, this is done using a parallel pattern simulator. Then out of these, some of the faults they will be in some of the change while doing this simulation, it is done in a differential fashion. Okay, that is why this that is if the portion of a circuit changes, then only it will do. Then after that it will go back to this, it will go back to the again it will start with the next P2 and start with the good circuit and insert faults one after other, inject fault one after other, and that way it continues. So, start with the collapsed fault list, it gets the next pattern. So, restore good circuit state, because we know the good circuit value. So, that is there. Apply the pattern, apply the next pattern. So, we have the good circuit output. So, this much is fine. Then it will see if we have any more fault to be simulated. So, if some fault is there, it will get the next fault, restore faulty circuit state. So, now this fault has been injected into the circuit and remove last fault. So, whatever fault we had simulated last time, so that is removed. So, this fault is getting injected into the circuit. Now, OF is the faulty circuit out response, and store the gate differences. Store the gate differences means that wherever the gate outputs are differing, so those gates are only remembered. And then we see that whether this the output response is same as good response or not. If they are not same, that means this fault F has been detected. So, it goes here, takes up the next fault and continues. So, in the simulation process, this gate difference value is there. So, that is actually going to help us in doing the simulation less. When the fault list becomes empty, then the fault list is there is no more fault, then it will be coming to this one and it will see, it will pick up the next pattern and it will try to simulate for the remaining faults in the circuit. So, this way it continues. Advantage, it is suitable for sequential fault simulation. Disadvantage, the order of events caused by faulty sites is not same as the order of timing of their occurrence. So, what we mean is that this order of timing of their occurrence means they have got some order in the circuit when this circuit when we try to simulate one particular gate, its predecessor must have been simulated and all that. So, but that is not happening. So, it is putting wherever the gate difference is coming. So, it is noting that. So, that sometimes create problem in the simulation. So, simulation has to be much more careful because of those bad gates that are the difference gates that are created. So, these differences are going to be again sorted based on time, and then the simulation has to be done. We will continue in the next class.